Hi there, my name is Matthew Berry and I'm a Raman application scientist at Edinburgh Instruments. In this virtual demonstration, I'm going to show you how to use the RMS1000 Confocal multimodal microscope to perform Raman and fluorescence lifetime imaging on the same sample with the same software. Integrating spectral and time-resolved imaging is beneficial because it allows you to analyse a broader range of samples and do in-depth dedicated studies of single samples. I will walk you through each stage of the process from turning on the system to presenting your Raman and FLIM images. Let's get started.
We begin in the Ramacle home screen. And the first thing to do is ensure that a region of interest in our sample is in focus underneath the microscope. This sample is a phosphorescent OLED underneath a glass cover slip. We will focus through the glass and onto the emissive layer. Once the sample is in focus, we have a variety of options for proceeding with analysis. The pink button with the wave number symbol will direct you to a spectral measurement window where you can detect Raman and PL spectra on the CCD. The blue button with the tau symbol will direct you to a lifetime measurement window where you can acquire decays using the photon counting detector. We would not recommend performing Raman measurements prior to FLIM because the more powerful Raman laser can photo-bleach the sample. To find the emission maximum within the sample, we will click the spectral measurement button and acquire PL spectra from the sample with the same laser we would use to record lifetime measurements, which in this case is the 405 nanometer HPL. PL spectra across the region of interest show peaks at around 613 nanometers, which is the emission wavelength of the OLED under operation. The blue region's PL is redshifted and less intense than the red region, which we assign to attenuation by the overlying ITO electrode and charge extraction layers in the blue region. We now know what wavelength to centre our grating at for the photon counting detector in FLIM mode. We can now close the spectral measurement window and open the lifetime measurement window. We will first increase our laser power and centre our grating at 613 nanometers. We can see the signal rate from the laser and the emission rate from the detector. And when we open the laser shutter, the emission count rate should be high, given that we have centered our grating at the emission wavelength of the sample. This sample is phosphorescent, so MCS is the better mode to use because it can acquire longer lifetime decays faster than TCS-PC. We click on MCS and make sure to set the repetition rate of our laser to external trigger mode, which means that it's now operating in MCS mode as well. When we probe different regions of the sample, it appears that the lifetime is changing across it, which means that it's an interesting sample to explore using FLIM. Once we have all of our spectrometer and timing conditions optimized, we can perform mapping in 2D, 3D, or over a complex surface, as my colleague Dr. Nikesh Patel recently showed with a tablet in his feature highlight on RaFLIM. For the purposes of showing how the software works, we will just do 2D mapping here. To create a FLIM image, we click on the microscope image and drag to create a mapping area. And then we can set the number of pixels within the image, either by telling the software the number of points, or our desired step size between points. We are then required to perform an initial measurement as a final sense check, and then we can start collecting the image. We have 4 panels in the map acquisition window. The top left shows an intensity image using the peak count rate. We will generate the lifetime image later in post-processing. The top right shows the count rate per mapping point. This is useful in TCS-PC mode because it shows if you are going over the 5% count rate to repetition rate threshold, over which pulse pileup can start to occur and decays become artificially shortened. In MCS mode, we do not have to worry about this threshold. The bottom left panel shows the 20 most recent decays, and the bottom right just the most recent. When we scroll across our map, it's clear that the decay can be characterised by an extremely quick scattering or fluorescence event, followed by a long phosphorescence tail. We will perform tail fitting on the decay to characterise the phosphorescence lifetime and how it changes across the sample. We can select the time range over which to calculate the decay and the number of exponentials for fitting it. Here, the decay follows a straight line, so we should only need one exponential. Let's now open the Lifetime Analysis tab on the right hand side of the screen to see both the calculated lifetime and the quality of the fit. A chi-squared value of 1.135 tells us that this is a good fit, and the value τ1 tells us that the lifetime at this point in the sample is 728 nanoseconds. If we click on some different points, we see that the chi-squared remains close to 1, so a single exponential fit is a good one for this image. Now we can generate a lifetime image where each pixel is the lifetime value at that point. We can change the colour map and enable interpolation between pixels in the image. It is clear from the image that the lifetime is becoming shorter in the blue region where charge extraction layers and the ITO electrode are present, which is strong evidence for more efficient charge extraction. To get some structural information from the sample, let's now generate a Raman image from the exact same area as we did for FLIM. To set up the system for a Raman measurement, we can change the laser power and grating within the software. Here we are going to use a 785 nanometer laser and a 1200 grooves per millimeter diffraction grating. We will center the grating at 1000 wave numbers and set our spectral exposure time. We can now acquire our Raman image. As the Raman image acquires, we can see that at every point in the image we get some fluorescence from our glass, but running up the boundary between the two distinct regions from our FLIM map, we have spectral signatures from some kind of organic substance, which we assigned as a mixture of araldite and epoxy resin. We can now generate Raman images based on peak intensity, area, width, or spectral similarity algorithms such as the Pearson correlation. This combination of Raman and FLIM is highly powerful in semiconductor research, solar cell research, and in biology.
So there we have it. We now know how to do Raman and FLIM imaging on the same sample using the RMS1000 and Ramacle software. We hope you found this video useful. For more on Raman and fluorescence, please like and subscribe, and all the best with your Raman and fluorescence research.